Hi everybody and welcome to another video of the Optimization Masterclass. So this class is going to be based on the course that I do at Imperial College, which is based on this book, Convex Optimization, of Stephen Boyd and Lieven Vandenberger. If you haven't followed the previous lectures in this series, please check the link over here. Remember that you can download the material that I use to teach the class, so the so-called smart handouts, from the link in the description down below. If you have suggestions on future topics that you would like that I cover in this masterclass, please leave it in the comments below. Thank you very much and enjoy the course. We now look at some generalization of convexity. So let's start with the first one, which is quasiconvexity. The reason why quasiconvexity is useful is because quasi-convex optimization problems can be rewritten as a family of convex optimization problems. That means essentially that we can still solve quasi-convex optimization problems with exactly the same tools developed for convex optimization. It's just that we need to solve multiple problems, okay? So we have to repeat we have to repeat the algorithm several times. So that means that, of course, computationally, this is going to be more costly. So to solve a quasi-convex optimization problem is going to be more costly in general than to solve a convex optimization problem. So let's look at the definition, okay? So a function f is called quasi-convex if its domain and all its sub-level sets, okay, are convex, okay? So it's very simple definition. And a quasi-concave function is, a function is quasi-concave is f minus f, so the negative, is quasi-convex, okay? Or otherwise, we can say that its domain and all its super-level sets are convex, okay? Again, we switched the sub for super and the definition is the same. We also have a definition of quasi-linear, which is a function which is at the same time quasi-convex and quasi-concave, okay? So essentially, if we look, for instance, at functions on R, so scalar functions on the line, essentially quasi-convexity is simply requiring us that each sub-level set is an interval, okay? It can be an infinite interval, but this has to be an interval. You cannot have two intervals, for instance, okay? Because let's look at an example, okay? So for instance, this is an example of quasi-convex function, okay? You see that, for instance, if we consider the sub-level set respect to this alpha, well, that's going to be, for instance, this set here. It's an interval, okay? And an interval is a line segment, and a line segment is a convex set, okay? So fine. Then we need to try this for all possible sub-level sets. So let's take, for instance, this beta here, and here the level set, the sub-level set associated to beta is essentially all the interval that goes from minus infinity to c. Again, this is an interval and it's convex, okay? So this is an example of a quasi-convex function. Obviously, this function is not convex because if I take a point here and a point here and I trace the chord, then we see that in this case, the function lies above the chord, and so this function is obviously not convex, okay? So as I said, quasi-convexity means simply on R that the sub-level set has to be an interval. What is then an example of a function that is not quasi-convex? Well, for instance, a function which has two bumps, like this. This is not quasi-convex, because if I check, for instance, the level set associated to this line here, alpha, then we see that the sub-level set is going to be this line segment here, but also this other line segment here. Then if I take a point in this segment and a point in this segment, and I trace the line segment between the two, you see that we are outside the set, because the set is this and this, not here. And so that means that this set is not convex, okay? So this is the meaning essentially of quasi-convexity for functions on the real line. It simply means that you cannot have more than one bump. I mean, more than one ditch. Okay, so that's the idea essentially. It's also possible to characterize quasi-convexity using a modified Jensen's inequality, or using the first order conditions or the second order conditions. Okay, so for what concerns the definition using the Jensen's inequality, f is quasi-convex if and only if two conditions hold, the domain of f is convex, and then for any x and y in the domain of f and every theta between 0 and 1, then we need to have this condition over here. Okay, so essentially the difference with respect to the standard Jensen's inequality is that we have replaced the linear combination of f of x and f of y with the maximum between f of x and f of y. Let's look at an example. In particular, what we're going to do here is first we're going to represent the chord, which is what we will do if we wanted to check convexity. And we see that in this part the definition of convexity is satisfied because the function lies below the chord. And then if we compare it with respect to the maximum, then we see, of course, that the function lies below the maximum. So if this shows that if convexity is satisfied, then for sure quasi-convexity is satisfied. Now we look at a more meaningful example in which instead convexity is not satisfied, and in fact if we trace the chord we see that the function lies above the chord. But if we then look at the maximum and we trace the maximum, we see that the function is below the maximum. And so even though convexity doesn't hold, quasi-convexity still holds. Like convexity, quasi-convexity can be characterized by the behavior of the function on lines. So it means that if you have a high-dimensional function and you want to check if it's quasi-convex, you can restrict it on a line starting from a point in the domain. And if the function is quasi-convex for all points on any line, then the original function is going to be quasi-convex. As I already said, quasi-convexity, like convexity, can be characterized using first order conditions and second order conditions. So for instance, if f is differentiable, then f is quasi-convex if and only if the domain of f is convex, and the second condition is that for all x and y in the domain, if f of y is less or equal than f of x, then we need to have this condition that the gradient transpose times y minus x has to be less or equal than 0. Okay, so what is the meaning of this definition? So when the gradient is not 0, the meaning is clear. Okay, so this condition that the gradient transpose times y minus x is less or equal than 0 is characterizing a scalar product between the vector gradient and the vector y minus x, and we have the property that f of y is less or equal than f of x. So essentially, this means that the gradient is defining a supporting hyperplane, okay, because it's essentially this inequality, as we already seen before, defines an hyperplane. So it defines a supporting hyperplane to the sublevel set associated to all the y's for which f of y is less or equal than f of x. Graphically, this means this essentially, okay, so that if we represent, these are the, what we have here, these are the sublevel sets of the function. In particular, this one here is the sublevel set as associated to the point x. Then we have that the gradient is defining a supporting hyperplane to that sublevel set. Okay, so that's the meaning of it. Now, remember that for convex function there is an important property that comes from the first order condition, which is that for convex functions, if the gradient is 0, then the minimum is a global minimum. Okay. That's an important property of convex functions, and why convex optimization is, I mean, one of the reasons why convex optimization is so useful, okay, because if you find a solution, it's actually the best solution to the problem. It's the global solution. This property does not hold for quasi-convex functions. Okay, so it's possible to show that even if you have a quasi-convex function, it's possible that the gradient is 0, but at x, but x is not a global minimizer of the function. Okay, so we need to be careful about that. As I said, it's possible to characterize quasi-convexity using second-order conditions. If you're interested, you can look at this, but I mean, it's not really. We're not really going to use this condition in the course. Okay, we're not going to use it. It doesn't mean that I cannot go back here and do it as an exercise or something like that. Okay. Moving on, if we consider now compositions of quasi-convexity, so there are some operations that preserves quasi-convexity and some operations that do not. Okay, quasi-convexity is preserved under maximum, supremum, composition, and partial minimization. But there are other operations that we have seen for which quasi-convexity is not preserved, and probably the most important one is the sum. Okay, so we would expect that sum preserves this type of properties. So we saw that sum preserves convexity, and it was, let's say, obvious that that was going to happen. But for instance, quasi-convexity is not preserved through the sum. Okay, and the example, I mean, the counter example is quite easy. If you take two quasi-convex functions, they have two independent bumps. If you sum them together, you can get a function with two bumps, and that's not quasi-convex. Okay. Let's now look at some example of quasi-convex functions. So we look at the log of x on R++. So we know that log of x it's a concave function. And apparently, you can show it is quasi-convex, is quasi-concave, and so is quasi-linear. Okay? So, yeah, I mean, it's not so obvious what a function, if a function is going to be quasi-convex or quasi-concave and so on. Okay, I mean, you have to sit there and think a bit about the sub-level sets of the function. Okay, so in the case of the log, you have this function like this, and we know that if we look at the sub-level set, you're going to have intervals, okay, which are open on the left hand side, but they are just intervals, and that means that this function is quasi-convex. Okay. Something a bit more complicated, the ceil function, the ceiling function, if you want, essentially is the smallest integer number which is greater than a real number x. Okay, so essentially you approximated a number to the closest integer above the above the number. So for instance, 2.2 is approximate. Ceiling of 2.2 gives you 3. And this function is quasi-convex, quasi-concave, and so it's quasi-linear. Let's look at another example, which is the function x1 times x2 on the domain r plus squared. This function is not convex and is not concave because the Hessian, if you compute it, is indefinite. Okay, I mean, x1 times x2 is a typical example of saddle point, and this is associated to an Hessian which has one positive and one negative eigenvalue. But it turns out that you can show that the super level set of x1 and x2 are convex, which implies that the function is quasi-concave. Okay, just be careful about the fact that this is a definition of, that is, I mean, this is true on r plus square and not on all r square. Okay, I think the last example that we're going to see for this class of functions is the following. Okay, so we have f of x, which is the ratio between these two affine functions. Okay, and this function is quasi-concave, quasi-convex, quasi-concave, and so it's quasi-linear. And the way of showing this is actually quite trivial, because if we write the alpha sub-level set of this function, that is going to be all the x that satisfy this inequality and this other inequality over here, in which essentially we multiply left and right by the denominator, okay? But these are just two inequalities, and so this set is just the intersection of two inequalities, so the intersections of two half spaces, and we know that intersection of two half spaces is a convex set, okay? So again, this is a quasi-convex function. Now, as we said, quasi-convex functions are useful because we will see that there are, quasi-convex optimization problems can be rewritten as a family of convex optimization problems. The way of doing this is based on the fact that quasi-convex functions can be represented with a family of convex functions, and that's what we're going to see now. Okay, so what we want to do essentially is to find a family of functions. Okay, so a family of functions is essentially functions in which one parameter is free and we can change and tweak that parameter. So a family of function, okay, which we call phi of t, so t is the parameter, okay, which we can use, okay, to characterize the sublevel sets of a quasi-convex function f, and that's because the sublevel sets are convex, okay. So what we look for is a phi of t, okay, so phi t if you want, okay, which has the property that when f of x is less or equal than t, then phi of t is less or equal than 0, okay? So that we know, this, we know that if ft is less or equal than 0, then f of x is going to be less or equal than t, okay? Of course, we want that this phi t satisfy the following property, the property that for all x, okay, if phi t is less or equal than 0, then phi s has to be less or equal than 0 if s is greater than t, greater or equal than t. And that's because, we want the property that, of course, if f of x is less or equal than t, if we take an s which is bigger than t, then for sure f of x is less or equal than s. And that means that we need to have that phi s still less or equal than 0. Okay, so this is an obvious consequence of the fact that we want to construct a function like this. Okay, but the point is, why we're spelling out this property, because this property has a name, and essentially, it's not as a name, but it's easily achieved if phi is a non-increasing function of t. Okay, so now we know that we want this property and we want that phi t is a non-increasing function of t. And a family with such a property is defined, for instance, in this way. Okay, so phi t is defined as 0 when f of x is less or equal than t, and infinity otherwise. Okay, this representation is not unique. You can come up with different representations with different families that have this property. And often what we would like is a representation which is differentiable, because we know that whenever we have differentiable functions, things are easier. Okay, let's look at an example, because I suppose that up to this point maybe this is a bit confusing, but once we look at the example, things will make more sense. So we consider a function f of x defined as the ratio between p of x and q of x. This function is defined on the convex set C. P of x is greater or equal than 0 and is assumed to be convex. Q of x is greater than 0 and is assumed to be concave. And it's possible to show that f of x is quasi-convex. Okay, f of x quasi-convex. So if we want to construct a phi t which has this property, well, a possibility is, we look at the following property. We look at the fact that if f of x is less or equal than t, well, of course, this implies and is implied by the fact that p of x minus tq is less or equal than 0. We just said, p of x divided q of x less equal than t. Okay, so p of x is less equal than tq of x, and this is what we have here once we bring this guy on the other side. Okay, this means that we have exactly what we were looking for, so this type of parameterization, if we define the function phi t as p of x minus tq of x. Okay, And we see that for each t, phi t is convex, okay? And for each x, phi t is decreasing in t. This is what we were looking for. And this concludes the example. We will come back to quasi-convexity and the way in which we actually use this representation later on in following lectures, in which we're going to solve quasi-convex. I mean, we're looking at the fact that quasi-convex optimization problems can be solved using convex optimization. And this essentially preliminary theory that we establish now we will be used more later on. The next generalization that we're going to study is that of log-concavity. So let's delve immediately into the definition, and then we comment on it. So a function f is said to be log-concave if the function is strictly positive on all x in the domain, and log f is concave. Okay. Similarly, we say that a function f is log-convex if it's strictly positive again, and if log f is convex. Okay. It follows that if a function f is log-convex, then the function 1 over f is log-concave. That's obvious because the definition involves the logarithm, and we know that the relation between convexity and concavity is that you can switch the sign and you go from one to the other. So for when the logarithm is involved, the switching of the sign becomes going from f to 1 over f. Okay. We need to notice that here the main definition is actually that of log-concavity rather than log-convexity. The reason is that log-concave functions naturally arises in problems which are maximization problems. That's why we look at the concavity rather than the convexity. Okay. Indeed, if you look at this definition, I mean, this is nothing special. I mean, essentially, we are just giving a name to the fact that to the fact that some functions are logarithmic functions, and then we call them. If once you take the logarithm of a function that becomes concave, then we say that the original function is log-concave. So it's definitely nothing special. We could just use the standard theory of convexity and concavity. However, there are many applications, and in particular statistical applications, in which there is the probability involved, in which the functions normally are logarithmic functions, and normally we have problems that in which we want to maximize. Like for instance, we want to maximize the probability. So since this application is so common and it's so common to deal with logarithmic maximizations, that's why that's why it's common to give this special name of log-concavity to these functions, and to develop a theory which is a theory of log-concavity. So speaking of this, we can say some things about log-concave functions. So log-concavity can be characterized using a Jensen's-like inequality, and this is going to be the following. So given a function f, which is strictly positive on the domain, again, we need to compute the logarithm, so we need that the function is strictly positive. This function is log-concave if and only if this sort of Jensen's inequality is satisfied. So what are the main differences with respect to the standard Jensen's inequality? Well, here we have the greater equal, because we're looking at concavity rather than convexity. And then here, instead of having the arithmetic mean of f of x and f of y, we actually have the geometric mean between the two. Okay, again, because we are working in the logarithm. Once you take the logarithm, this becomes arithmetic mean. Okay, so this should be obvious. Let's look at some examples. Okay, so the affine function f of x, which is given by x transpose x plus b, it's obviously log-concave y in its domain. Why? Well, because we know that log x is a concave function, and an affine function behaves well with respect to concavity and convexity, and so we know that the log of a transpose x plus b is going to be concave. For the same reason, we can easily study x power alpha. If we compute the log of x power alpha, this is going to be alpha, the log of x, and we know that the log of x is concave. And so this means that if alpha is non-positive, okay, so negative, for instance, then we have that these all things are, it's minus a concave function, so it means that it's going to be convex, so the function is log convex. Instead, if a is greater or equal than 0, so it's non-negative, then the sign doesn't change, and so that the function is log concave. The exponentials, well, I mean, if we compute the log of e power ax, this is just ex, and that means that the function is going to be log convex and log concave, because ax is a linear function, so it's a special case of affine function, and affine functions are both convex and concave. More interesting examples, and the reason why we actually study log concavity, are the probability densities. Okay, so many probability densities are log concave. For instance, the normal distribution, the cumulative Gaussian distribution, and the uniform distribution are all examples of log concave functions. Okay, log concavity can be characterized using derivatives, and for instance, the second order condition using the Hessian is given over here. Okay, you can look at the handouts if you to read more about this. I'm not going to spend too much time about this because it is always the same story. Okay, so yeah, the formula changes, but the ideas are the same. What is interesting is that, and I mean, it should be obvious, but let's point it out, is that log concavity is preserved under product, okay, and a special type of integration, but is not preserved under addition, okay? So this should be expected because the logarithm behaves well with respect to product, but it does not behave well with respect to addition, and that's why it's this carries on the log concavity. The last generalization that we look at is that of convexity with respect to generalized inequalities. And these definitions are obvious. It's essentially the same as standard convexity, but we are using generalized inequalities instead of standard inequalities. Okay, so that means that we need to have a proper cone K, and to this proper cone K we can associate a generalized inequality, less equal K. Okay, so with this symbol. And then a function f, which is going to be a function of that is going to give it has m components. Okay, so it's a generalization with respect to what we saw before, because the functions that we saw before are all functions that go from Rn to R, and in this case we go from Rn to Rm. So f, the function f is said to be K-convex, okay, so convex with respect to the proper cone K, if the Jensen's inequality is satisfied. And the Jensen inequality in this case is exactly the same as the standard inequality, but we have the generalized inequality there, and we can give a similar definition for strictly K-convex, in which we have the strict generalized inequality. Similar definitions can be given for K-concavity, and of course when K is equal to R plus and M is equal to 1, then this generalization reduces to the standard definition of convexity and concavity. Okay. Many results that we've seen for convex functions holds also for K-convex functions. For instance, we can study the K-convexity of a complex function by studying the behavior on any line passing through the domain, so like for standard convexity. And the K-convexity can be characterized using first order, second order conditions. Now, of course, this generalization of convexity with respect to generalized inequalities is important because it's important essentially whenever we have functions which have m components. Okay, so for more complex problems, we expect that we will use this type of this concept of convexity rather than the standard concept of convexity. But the point here of this lecture is just to say that, you know what, is exactly the same. I mean, it doesn't matter if we're looking at convexity with respect to a proper cone, which is not the standard R plus, still everything holds, and still we can use actually the standard theory of convexity. Okay, and so we can solve those complex problems. Let's look at one example. So we can look at the function f of x defined as x squared, where x is a symmetric matrix. Okay, so this is a function f that you see that goes from the space of the set of symmetric matrices of dimension m times m to the symmetric matrices of dimension m times m. Okay, and this function f is s plus m convex. Okay, and we can show this, and the way of showing this is essentially looking at, I mean, we apply the Jensen's inequality, okay, on the linear combination of two matrices x and y, which are symmetric, and we end up with, you know, I mean, this expression here, it's a quadratic expression which is less or equal than you know, the mean of the two individual squares. Okay. And this shows essentially that this term here, so this matrix on the left hand side, is less or equal with respect to the standard inequality on the space, which is the S plus cone, than this term here. Here I'm missing a theta. Okay. Which means essentially that the function that we are considering is indeed convex with respect to the cone which we're using. So the cone which we're using, as I said, is the S plus cone.